If it's visible, I'd like to continue.
Yeah, we can see it.
Thank you, dear Chairman, and also thank you very much to the organizing committee and also the attendees. It has been a long time. You have been waiting. I don't like to keep you much longer. Here, I'd like to present a study a little bit different in perspective than the previous ones. I'm originally mining engineer, near processing researcher, and also currently interested in plant designs and also feasibility studies. And I'm working with a team of geologists, very experienced geologists, Professor Ömer-Gecek, Can Başaran, and also we have...
Chairman, can you ask the speaker to speak into the mic? Can't hear anything.
Really? Is it better? Can you hear me?
Yes, we can hear you, but you can just keep closer to the microphone a little bit.
I'll try to. Thank you very much for this. So I'd like to give you a different perspective than the previous researchers, because as I'm a mining engineer, I'm totally interested in the value of lithium in water. So the question is, why lithium is, here it is, why lithium is important. We have now three key points. Those are like, we have new Green Deal agreement that Turkey is agreed to fit in, which means zero carbon emissions by 2050. And also, there's another point that currently 65% of global consumption of lithium is for energy storage devices all around the world. And there's a projection regarding to this usage. The annual car sales for the year 2025 is projected as 10 millions. For 2030, it will be 28 millions. And 2040, half of the overall car sales will be electrical vehicles. So keeping this in mind, the 65% of global consumption of lithium on the energy storage devices, so it will be tremendously high that we will see the increase in demand. And I'm changing the screen. Could you follow this, or is there any lag?
It is still the first introduction.
Really, I have already passed the tree. 1 sec. Okay. All right. So this is the introduction why lithium is important. This is the graphic that I would like to share with you. Sorry. This is the projection of lithium demand is very crucial for us. There's a European Commission report that has been presented like a year ago, and there was a discussion about the lithium. It's a critical raw material for European commissions, and they have this prediction like they have the demand increased by 56 times by the 2050. So at this point, I would like to say to you that if this much lithium is required, so what is our position? Where do we find lithium in Turkey? So in general, lithium is mainly derived from the different geological resources, as we may say, and it is like in minerals such as spodumene and lepidolite, clays such as hectorite, salt lakes, and underground brine reservoirs. The lithium is found in many forms, but most of the produced lithium is like 66% of global lithium reserves found in these brine reservoirs, and the lithium is contained in salt waters, lakes, cellars, oil field, and geothermal brines. Well, let's come to Turkey. So what is the situation in Turkey? We have two major points for these resources. Unfortunately, we don't have economic ore beds for lithium in form of spodumene and lepidolite, but we have this lithium in boron process waste in Kırka, Eskişehir, So they have extracted already, and they have a pilot plant that I have already visited, and they are making some sort of lithium carbonate production. And also, I'm aware that there are some test runs performed by research groups, and also Professor Baba, I'm very fond of him, doing this sort of lithium gains from geothermal brines currently running in Turkey. So, as we say, we are lacking resources for lithium, and what's more, we are talking about what we have been performing in Afyon. So even Afyon has very small amount of lithium in the geothermal brine, like at the tops, like 3.5 ppm, very low, very low lithium content. We are aiming to work on Afyon water, because in Afyon there's all around the year production. There is this tourism all year round, summer and winter, and also there's electricity production for the city, and also they have this municipal heating in Afyon city. So they have a huge amount of water extracted from the ground. So the process is feasible in terms of all year production. They have high production yield when it comes to the heating of the city. They take out like 900 tons per hour of water extracted from the ground, hot water extracted from the ground. This is high production yield, is very important. And also we have a research team who has already examined the area very well. So depending on these points, we may say that starting with Afyon, it's a challenging job with a 3.5 ppm lithium, but also it's also very encouraging with an offshed firm which is backing the project, and also the city council is backing the project, and they are really wondering the results of the outcome of this study. And this study is, I may say that it is like the pre-feasibility study, right? So our findings are like, they're not dynamic solutions, but they are static answers of to be given at the preliminary stage. So keeping this in mind, I would like to continue with the presentation. In materials and methods, we work in field studies. Those contain geologic and hydrogeologic investigations, geophysics investigations, geothermal water sampling. To make this research, to make this feasibility study more dynamic, the sampling should be all year round, and also the alternating areas should be checked in terms of the lithium origin. So this part is very important, but our article was not focused on this area. The next thing is our article is mostly focused on the lithium capturing unit, the absorbent. It is mangan-based inorganic absorbent, very sensitive to lithium ions. And what we are interested in is, could we produce this absorbent, selective absorbent, just checking out the literature, is it possible to produce in Afyon? So this is our greatest achievement, that we have already produced this absorbent, and also the best performing form of this absorbent according to X-ray analysis. We may say that at this point it was very successful study. So continuing to materials and methods, so this mangan, lithium-based mangan inorganic absorbent produced, and it was characterized by X-ray diffraction. Then also we have SEM images, and also surface area analysis, which is very important for characterization for mineralogical, morphological, and physical. And also we need to make some absorption tests. We have two types of absorption tests, which is batch-wise and column absorption test. In order to quantify our absorption success, we have to do this. And here I'm presenting you the XRD graphics, if it stays. One sec. Here. This graphic is the...
Dr. Can, we are still seeing the introduction slide, which is fourth slide of your presentation.
Really? I'm coming back again. Wow. Fourth slide. Okay.
Yeah, you have to click from the left panel on the slide that you would like to switch to. Don't use page up and page down buttons.
Sorry, do you see now the materials field
Yes,
studies?
we now see the materials and methods.
Sorry for that. Well, now I'm coming to materials and methods about the absorbent characterization. Here I'm presenting the XRD graphics. Is it on?
Yes, it is.
So this is the most important part of the paper. Here on the left we have this XRD graphics of our produced absorbent before and after acid treatment. When our absorbent is acid treated on the left side, there is a peak shift to the right. The red one at the top, you see, it is lithium manganese oxide. The bottom one is lithium minus hydrogen oxide. So at the top, the material is prepared, and after the acid treatment, the peak passed to the right side. So it means that the cubic structure has shrinked, and it is now ready to, the lithium has been replaced by hydrogen ion, and now the absorbent is ready to catch the lithium in the water. It's very highly selective cage, and it can only be replaced by hydrogen or lithium. If the and also by this structure here at the bottom, we are presenting the percentages of our produced lithium mangan hydroxide, and we have at the next slide. You may see a SEM graphic now, right? And by this configuration, XRD configuration, we have the chemical formula, exact chemical formula, and we have matched it with the literature. And also, with this match, we have found out that our bed area has been like 53 square meters per gram, which represents that we have high surface area, which could get into contact with the water, geothermal water containing lithium, and make an exchange, by the way, and get the absorption of lithium on these surfaces. And also here is this SEM images representing the pore structure of our presented surfactant. So we have like mineralogically confirmed that our material is what it is, but now we have to show you that we have to show that it can do the lithium absorption. Now we have two graphics on the page. I hope we have these graphics. And on the left, we have three composition of this mangan lithium spinel to be for absorption. As it is by the production of the absorbent, it requires a part that to make the structure. So we use in these terms of sodium silicates to make the form, rigid form. And we now on the graphic you are seeing that 19%, 24%, and 30%. Those are the amount of lithiums, amount of sodium silicates used for the formation of the beads. Now, we have formed these beads and at 650 Celsius degrees, and we have these rigid forms, and then we have this absorption test performed. here we go, and as you may assume that the less sodium silicate used, the higher capacity for the material to absorb lithium. But the result is true, but as we are designing an absorption column, during this test, it should keep its physical form contact. So we have, in our preliminary test, we have found out that the lack of usage of sodium silicate resulted in the fault in physical structure. So it was not usable. So the most rigid one was the 30% weight percentage containing sodium silicate beads were the efficient ones to perform in physical form. So right after this study, we have to make it to kinetic study for the absorption. So the graphic on the right has been produced. We have the absorption performed at 1, 2, and 5 ppm lithium bearing artificial waters, and the time was up to 24 hours. And the next experiment was column test. This is a normalized lithium absorption rate by bed volume column experiment. And here we are working with the artificial sample and also geothermal water sample. And at the bottom, you may see that these data referring that we are sending the 3.5 ppm lithium bearing water to the column, and each bed volume period, we are collecting the water and sending it to the lithium test. We are not receiving any lithium. So it means that 100% of lithium in water has been captured by the absorption column. Up to here, we have 66 bed volume. As you may see at the end of the graphic, it is. At this point, the 10% of 3.5 ppm lithium has extracted from the column. So this is, we call it the point of failure. So the absorption column has performed its work. At this point, the water should be sent to second column, and this column should be sent to regeneration and for production of lithium carbonate. So this is the graphic. And also, when we have this graphic, these values should be converted into numbers for evaluation of the success for plant parameters. Here we have scale-up calculations for absorption rate. This is pseudo second order absorption kinetic equation, which we have performed, and also it has high R-square values, which we thought that it was okay to continue. And the second part is we have scale-up calculations for column experiments. Those equations are very, very simplistic equations and very common in plant design for absorption columns. So I'm going faster, by the way, to come to this results. I hope you may see this discussion point page. Is it on?
Yes, we see the discussion page now.
Okay, it's very well. So at the end, the geological parameters, we found out that such as structural composition of the reservoir rock, composition and circulation time of the geothermal fluid, type of recovered material, fluids, larger in scale, and type of valuable materials in geothermal systems are effective for the determination of lithium recovery methods from geothermal resources. The second one is absorption methods have advantages such as cost-effective for extraction of lithium from brine. We have high chemical stability and high lithium uptake capacity, and being environmental friendly, we have low toxicity. And the next one is lithium mangan spinel absorbents have superior lithium selectivity, high lithium absorption capacities, and excellent regeneration performance. So there are many studies about their absorption capacity and crystal structure, and one of them is ours. The next one is the absorbents may not be optimum until they are tested with the original lithium ion source, because nature delivers water with unique ionic composition at any location and environment. So with keeping this in mind, we have these conclusions. So the lithium ion selective beads, well-known mangan lithium spinners, we have prepared and tested, and we have seen their performance with this Ömer-Gecek geothermal waters and also artificial waters prepared at 3.5 ppm. And the last one is according to fixed bed absorption column parameter scale-up equations, and we found out that for a ton of adsorbent, 1.63 tons per hour feed of geothermal water, we can obtain 236 grams of lithium ion, which when we convert them into lithium carbonate, this number goes up to 2.5 kilograms in 41 hours. Here we come to make a calculation. So each ton of adsorbent can gather 2.5 kilograms of lithium carbonate at 41 hours. If we exaggerate this number, we may exaggerate this number like statically, static models, and we may say that we can come up to like 20 to 25 100 kilograms of lithium carbonate. This number is crucial because the Ministry of Energy has declared that Turkey has a consumption of 12,000 kilograms of lithium carbonate per year, and their facility in Kırka production number is around like 10 to 20 tons per year, and they were proud of it. And up to these numbers I have calculated, we may assume that 3.5 ppm lithium-bearing Afyon waters can produce 20% of annual need of Turkey for each year. This is my final conclusions, and thank you for your attention and also patience for listening to me.
Thank you, Dr. Can, for your presentation.
Thank you very much.
There are no questions in the question and answer panel, but do we have any from the audience over here? Okay, thanks a lot.